So the third talk today will be delivered by Professor Pierre-Louis Lyons with the title On Mean-Field Games. Professor Lyons is professor at the Collège de France, and he is a member of Academia Européenne and the French Academy of Sciences. Professor Lyons has received numerous awards, including the prestigious Fields Medal in 1994. So may I now invite Professor Lyons to the stage. Professor Lyons, please.
Thank you. Well, I'm still trying to recover from Serge Arrau's stroke. So, especially being a mathematician, coming after him, where he explained how physicists in the 20th century progressively unraveled the mysteries of the universe. What I'm going to present will look much more prosaic, and our goals are certainly much humbler. However, at my very modest level, I can only agree with the big message about the interplay between applications and theory, each fitting each other. This I can see that at my modest level. So today we have this special session of this Hong Kong-French cooperation, scientific cooperation, and we are honoring Philippe Ciarlet. He's nervous. He's getting nervous because no one can control what I'm going to say. There was no way I could avoid coming. There is no way I can say no for something which concerns Philippe. Because after all, a few years ago, he was my teacher. He was one of my teachers, but a very remarkable teacher. It was a few years ago, 75. So 43 years ago. Once you have followed his classes, his courses, you are not the same afterwards. It's so clean, so perfect. Even the colors are perfect with chalk, not with computers. Well, that's easy to do. Not for me, but for the majority of people, it's just perfect. In fact, it's so perfect that it becomes suspicious. I'm sure that a psychiatrist would get worried, saying that the quality of your blackboards and the organization of your classes. Yes, indeed, that was pretty amazing. Although part of his class was being done by Vivek Giraud, as you might remember, and which included a really computing thing, because it's good and nice to do theoretical maths, but at the end of the day, you often have to compute. But of course, in 75, computing, this is just a matter of education for the young students. So we were using perforated cards. And any tiny error in perforation would mean that the batch of cards that you would give every evening at a special place in the university would come back the following day. And of course, no computation was made because there was a tiny perforation error. So I remember spending hours because of his class, just trying to find the mistake in the perforation. That was a time very well employed. But anyways, this was in fact very useful to do real computations. Philippe is someone that has always marked me and impressed me. John already mentioned some important mathematical achievements, but I have to confess that the thing that always impressed me most is the only person I know who knows how to open a champagne bottle with a sword. Back. So, and I think we should ask him a demonstration today. I mean, that's something unique. I'm not sure you have ever seen that, how to open a bottle with a sword. And, you can still do it? You say, of course. And I've always been very jealous. Now, that's one more indication, because of champagne, yes. He likes champagne a lot. That's a message. Really a lot. Really a lot. Okay, I think it's time to stop. He's getting nervous. No, I'm not saying he's a drunkard. Well, no, he likes champagne a lot. Anyway, so yeah, there is no way I could turn down the possibility of honoring him, and it's always a great pleasure to be back here because, in fact, I've been not frequent but regular visitor, and I've been here many times. I don't know, 6 times, 7, I don't know. We are too old to count, and mathematicians cannot count. I mean, that's one thing you should. By the way, I understand that not everybody in the audience is a mathematician. Don't worry. You know, one of my great heroes, John von Neumann, said a few things about maths. The first thing is, if you're worried because you know very little maths, relax. No one knows any maths, including mathematicians. Let me prove this statement. When asked, how much maths do you know? That was late 20s. John von Neumann immediately answered. He was always answering immediately all the questions because he had always thought about the questions beforehand. So he immediately answered 28%. So that was the late 1920s. That was John von Neumann, who was absolutely incredible mind. And he said 28%. Of course, that's a joke, but that means that he didn't claim that he understood more than a quarter of mathematics in the late 20s. And since then, mathematics have exploded. So if a given mathematician understands 1% of mathematician, he has a huge spectrum. And most would understand maybe, I don't know, hundreds and millions of maths. So relax. So really understanding maths is difficult. That's one thing. In fact, John von Neumann said something else about understanding maths. One never understands mathematics, one gets used to it. Okay? This may be true of many things, but it's particularly true in maths. So that's a good excuse for talking very little about maths. There will be from time to time a few equations. I have, this is a clean screen. One cannot write on that screen. I already want to destroy the, no, that's, okay, don't worry. I will use my hands. After all, I'm a Mediterranean, so I can use my hands. Well, anyway, so let me first show you a movie, okay? No maths. There will be a few bad-looking equations, but we'll go very quickly upon them. I'm going to talk about Winfield games again. Last time I gave one of those France, Hong Kong France lectures. It was about junctions. This time it's going to be about Winfield games, but some years ago I had talked here about Winfield games, but the subject has moved a lot, and fortunately I have to start from scratch. Okay, so the first thing I'm going to show you is something which seems to be very far from maths, very far from anything. Okay. So you see this. I'm not making any comments. Just look, it's slightly accelerated. But you see all this traffic. There's a lot of traffic lights, no organization, but it works. Thank you. That's so. Why am I showing this this video? It's in India. It's also the speed. It's slightly accelerated, right? To make it funny. By the way, if you learn anything from this lecture, it might be about this site Fun Mansion, where you can see lots of funny videos. I didn't find this video. Why did I show it? That's because of a collaboration with some engineers. And in fact, those engineers are the ones that showed us this video. And which engineers? They are telecommunications engineers from Huawei, and we have now a big operation with Huawei where they are sponsoring our research, and it's about the future mobile networks. Because in some sense, the mobile networks are going to look much more like this video than any kind of very nice American-like traffic when you have 4 stops, all the car stops and so on, traffic lights stops and so on. Or if you have even worse, I mean, that would be the French way, this was working. If you want to make sure it doesn't work anymore, you put a policeman in the middle, and then you're sure that traffic is going to be blocked, right? Because you're putting some kind of centralized intelligence in the middle of the intersection, although one might discuss what kind of intelligence is that. But anyway, so and you just cannot do it when you're saying that in the near future you may have, like by square kilometers, you may have like up to 2 million connected objects. So there is no way you can go inside the network and push up the information in order to organize the traffic. And you need to have decentralized intelligence. Okay? Well, decentralized intelligence, that's something that you may find in a crowd. So let me show you here some numerical simulations which concern another important subject, which is crowd motion. So nowadays, whenever you build any kind of public building or building where you have crowds, in many countries, you need to give, in order to have the authorization to build, you need to provide some evidence about how the building can be emptied in case of emergency. Minfield games, which is what I've still not talked about, have been used recently to provide such evacuation plans for the big towers which are being built in Dubai. Engineers, we discovered that by chance, and we realized that indeed they were using Minfield games in order to make simulations of how people on a given floor. It's not evacuation of the whole building. It's just evacuation of a floor. But on the floor you may have like thousands of people, and that's certainly a number which requires some modeling, and in terms of simulation it's not easy. There are commercial software which consider the crowd essentially like a fluid. And I'm going to show you the difference. Okay, so you might think that what you're seeing there is like, a concert hall or a movie. So you have the various rows, people sitting in each rows, and the exits are going to be located there. Okay? So a model where the population, the crowd, behaves like a fluid would be something like that. So it goes very fast. You have an increase at the end of the rows because you have obstacles with the chairs and so on. And after a while, everybody has gone smoothly out. Except that I've never seen people getting out of a concert hall in such a smooth way. For instance, the first thing you observe is that at the end of each row, you have a little block because there are more people here standing there before being able to use the lateral rows and exiting. Okay, so what's missing already in such a, the first layer of model making? What is missing is the effect of congestion. Okay, so let's add this. And all those things are easily made possible. Okay, so what am I saying here? I'm sorry, there is something wrong. I think I've selected. Okay, I know. Sorry about that. I showed the wrong one. Okay. So you know those spikes, you see those spikes which reflects various blockings. There were spikes, I'm not going to show, you had spikes here and also spike there because of two flows meeting near the corners, okay? And then I want to show you something which is even a little more complicated. I already showed it, but I want to explain it first. So it's going to be, even without congestion, it's going to be about the idea that, okay, you may not know which door is going to open. So that's what, it's an illustration of common noise. So you know that at some time here, the time is even random. One door is going to be open, possibly two doors are going to be open, you don't know. Okay. But what happens? Well, it happens what you people anticipate. Those are not fluid particles, and it's very symmetric. But at some point, that's the right door which is open, and then people first exit from the right and then the left. It's natural, it's common sense if you think about it. But of course, what you want is to have models, and you want to have a toolbox which is going to do that automatically without thinking about is this, or which are the phenomena that we should take into account. Okay, so mean-field games are indeed a new class of mathematical models that we started already some time ago with my good old friend and colleague and Jean-Michel Lasserie. Jean-Michel Lasserie is a unique mathematician in the sense that he is a part-time amateur mathematician. But he's one of the most inventive and original persons I've ever worked with. So he has always, he was a professor at Dauphine and then went in the private sector and had kept on doing R&D in the private sector while at the same time being extremely innovative. So it includes many, many other collaborators that I will mention later on. So what I'm going to do is, I don't know what I'm going to do, in fact. We'll see how it goes. We'll see how much time is, at what time should I stop? This is the first information I need. Good question, because that's lunch. Jean-Michel is, Jean-Marie is approving my request. At which time should I stop? No, that's a question.
1 hour.
1 hour.
40 minutes.
Okay, perfect. Unless I'm sure. I'm pretty sure that if I stop early, no one will complain. Okay, so what I want to do is a really simple example that will require very little math. A general structure, I'm going to show it. It's going to be just show all full formulas that will jump over it. And then I want to mention some current perspectives and overviews. Maybe I'll say a few words about big data, artificial intelligence, and so on, because there are connections, especially when we are dealing with data which is created by human people, and human people are strategic beasts, animals, which mean that those are active data, and if you don't incorporate the way they are going to react to what kind of games they are playing, and you're just analyzing blindly the data, you're going to miss the boat completely. So my point is that the post-artificial intelligence, which is really, because artificial intelligence is just a buzzword for a few easy problems which are being solved. I'm being very provocative. The next step will be to go after really difficult problems, and difficult, intrinsically difficult, not difficult because of the scale of the problem, the size of the problem. And this will require combining data techniques and modeling. And certainly we have a few examples in mind. But I just wanted to mention this now because I'm not sure I will have time. That's lots of blah blah. Don't read it. I'm going to simplify this a lot. We started this very early in the 2000s, and the fun part was that we immediately realized that there was absolutely no mathematical tools to handle the models that we were formally writing. So that was fun, because this meant that we had math to do. There are lots of applications. It has become itself a fashionable subject. Numerous applications in economics, in finance, social networks, crowd motion, telecommunications, fleets of automatic vehicles, in all situations where you're interested in issues about coordination and but also having decentralized intelligence. Lots of things, players / agents that can strategize, can anticipate, and make decisions. Why I'm saying it has become a fashionable subject is there are papers, a continuous flow of papers on this subject. There are, just in mass, probably in international meetings on Minfield Games every 4 months. And 3 books in 2018 and so on. So it's exploding. It's exploding in economics. Even I know 2 different groups of physicists who have started looking at those equations with some ideas coming from, because physicists are much better than mathematicians to, if they cannot solve the equations, to try to get some idea on how the solutions look like. And that's also very helpful, because the numerics are not easy. What are we trying to do? It's time that I start by saying what we are trying to do. New class of models to do what? Okay? To try to make mathematical models, descriptions of situations that involve lots and lots of small players. So lots and lots means that you have a huge number of players and that you're going to you're going to do the idealization, which is a passage to the limit, which is called a continuous limit, going to a continuum. Instead of having a large but finite number of players, you think that you have an infinite number of players. Point number 1. Small players. We are typically in a situation where a given player cannot influence by himself the outcome of the game. Okay? Although I will come back to that, there are new situations where we have a crowd of players and 1 big players or 2 big players, and that's also something that we can accommodate, which in game theory would be in the spirit of the so-called Stackelberg games. Okay, so it's, and the third thing is that all those players need to be rational. Okay, so rational is a word which is a very dangerous word, and I'm using it like economists do, which means that they are trying to optimize something. Okay, so in particular they may try to optimize, I don't know, their wealth if we are talking about economics or whatever. But they might also want to minimize the distance with respect to some kind of average beast. That's mimicry, that's herd behavior. Herd behavior can be thought in such a context as rational. It means that there is a criterion that may depend on the characteristics of the other players, that each player is trying to, being a mathematician, always minimize. Economists and finance people always maximize, or always minimize. But that's the same thing, so minimizing some criterion. Fine. So, in fact, when we started because we were sponsored, not by Huawei, but by 2 companies, namely Électricité de France and Crédit Agricole. Why? The idea was to see what kind of economical, financial tools / financial tools could help for sustainable development. So usually we think, and we are right to think, that finance destroys more, many things which are important for sustainable development. But more and more people are trying to reverse this process and to say, in the end, many questions about ecology, sustainable development turn out to be economical issues, economical questions. So how can economical theoretical reflections and mathematics help there? I may give later on some example, like how can one help a population to switch from one energy use to another energy use, and so on. Fine. Nevertheless, we started from scratch. We had no clue that we had to build new mathematical theories. Clearly, what the two typical characteristics of problems that involves, let's say, finance, to simplify, that's a very vague word, and sustainable development are long-term, okay? And as economists say, lots of externalities. Namely, you cannot think that you have one player which is a representative of a community and which tries to play his game as best as he can without taking into account the rest of the universe, which would be typically in terms of decision theory, that would be typically the realm of control theory, dynamic programming, Bellman-type equations, which was essentially the only tool that could be used by economists for many years. Okay? Externalities, modeling externalities, namely the influence, for instance, of others, the influence of a common, random environment, were something which couldn't take into account. Except that there were a few, as usual, the great Italian mathematician said once, in Italian, but I'll translate it, but it's, I think, pretty easy to understand. Chi cerca trova, chi ricerca ritrova. So who searches finds, who researches refines. So in some sense, that's true, especially for mathematicians, because very often some people had already some ideas before mathematicians. Who have those big luggage of, proving, that needs to carry those big luggages about proving something. That doesn't help to go fast. But anyway, so in economical theory, you have something which is called anonymous games, which is a very particular case. And then I was visiting Chicago. I invited myself. I know the people in the economics department. The economics department at the University of Chicago is one of the best worldwide. There is collections of Nobel Prizes in economics. Some are really reactionaries, but some are really smart economists. And like Bob Lucas and people like that. And I've known Bob Lucas. I was a professor in Dauphine for many years before becoming there. And it turns out that this is where it's basically a business school. This is where I learn how to speak to people in business school and people in economics. And I knew Bob Lucas. So I asked Bob, we have those ideas. I think it might interest economists. Can you arrange some kind of private talk or something? I didn't want to give a regular seminar, so it was just 10 people from the faculty and a blackboard and having some kind of brainstorming session and so on. And Bob Lucas was enthusiastic, and the following day came back and told me, Pierre-Louis, there is this paper by Krusselt and Smith, those two guys. I'm sure we never understood this paper. Nothing is defined, nothing, they make numerical simulation, they have a conclusion that we don't understand, which even are debatable from an economical point of view. It was a paper about macroeconomics. I don't have time to explain this paper. And his conclusion was, well, I'm sure it's a Minfield game. Can you explain this paper to us? Okay. So we looked, and it was absolutely incredible. So they didn't know how to define those objects, and you will see why. The mathematical formalism is much too sophisticated for them to write it. But they had the intuition. So they had this intuition of a huge population, that one should describe this population by a probability measure, that this probability measure will be evolving along some decision-making process. And so they never wrote any kind of equation, they just wrote rules for the players. Okay? How the game was being played. What were the random shocks, common random shocks? Maybe I have time to do that, but that's complicated to explain. And then they were doing simulations. So simulations in the end are about solving a partial differential equation in infinite dimension, in the space of measures. Okay? So how are they doing that? Well, what they were doing was Monte Carlo simulation on one end, which is natural for large dimension, but also you need to discretize the space of measures, and they were replacing a probability measure by the first 10 moments. Okay? So, and then there's this numerical procedure, which was perfectly valid if you knew what the model was. So the level of intuition which is behind this numerical procedure was astounding, because they had no clue about the real mathematical structure, but what they designed as a way to numerically compute in order to make predictions about this type of situation was perfectly okay. So their conclusion was 90% of the action of what was happening in that economical situation was depending only on the first 2 moments of the measures. And Bob Lucas, told me, I cannot agree with that. Economically, it cannot be true. So what is going on? I mean, and he was right. So it's not true that it depends only on the first 2 moments. But it turned out the level of noise which was assumed in the numerical simulation was relatively small, that the dependence in the first 2 moments is true if you have no noise, and so that the effect, that the majority of the effect was indeed depending only on the 2 first moments, was only due to the level of noise present in the system. So the end result is not that it depends only on the 2 first moments, as Bob Lucas had the intuition, but the numerical computations were correct, and most of the action is captured, indeed, by the first 2 moments. Fine. We have many collaborations with various economists, including Philippe Aguillon at Collège de France, José Schenkman, Columbia, Pierre-Noël Giraud, École des Mines, and this young guy, Benjamin Moll, who is just a rising star in economics, is really smart. And those people are learning, not Philippe Aguillon or Pierre-Noël Giraud, but they are learning, the young generation in economics is learning lots of math. In fact, Minfield games are already being taught in economics in the master's programs in many places in the States. Okay, so I guess we were lucky. Some written references, but most of the existing mathematical material to be found in the Collège de France videotapes. You know that Collège de France, we have to teach a new course every year. You may also know that those courses are being, most or some of those courses are being taped, and in fact, the courses are being looked, or at least downloaded, by many people. I think the average numbers, so it's a very effective way, the average numbers is 12,000 downloads per course, which is not bad. And in fact, all around the world, I find people that have been looking at my classes, and it's from Cuba to people in the traffic jams in LA, which are watching that on their iPhones. I've seen everything. So I suspect also that in my case, when I was giving in the last few years, I've not been really giving talks on min-field games on different subjects, but I suspect that there were also some young people downloading my classes because they saw in the title games. They must have been disappointed when they realized that there was no video game, but only a strange mathematician moving around the blackboard, on the blackboard without even using a computer. So they must have been seriously disappointed. So if you want to look at those things, you can, especially, as I always say, if you have trouble sleeping at night. So I recommend 5 minutes just before going to bed. Perfect. Costs very little. Okay. From a scientific point of view, those models are going to be a combination of something which is very often in statistical mechanics and statistical physics considered a very simple object, namely min-field theories, and the notion of mass equilibria in game theory. Okay? I think that's enough. Forget all the blah blah. Okay, little bit of mass. Very little. I'm going to take a simple example, which just to show how those models pop up, arise, which is a position game, a metric space. Forget it. Think of a line. Okay, we're going to go to the sea. This we can understand it. The sea, the beach is a line. And the game is where I'm going to put my towel. Okay, fine. So I have to choose a location. So you have n players going to the beach. They have to choose a location. Of course, the goal of this model is not to teach you where to put your towel. You know how to do that. But if everybody behaves in a similar fashion, we can accommodate several classes of people behaving in different ways. But if you have a relatively, as people would say in statistical mechanics, statistical physics, that the particles are indistinguishable in order to be allowed to write some min-field equations, you need those assumptions. Yeah, I'll come back to that later on. Similarly, if people are indistinguishable, which means that, Ciarlet is going to the beach, I'm going to the beach. If I'm being called Philippe or if he's being called Pierre-Louis, it won't change anything, right? So the labels are completely irrelevant. So this kind of symmetry and distinguishability, and each of those players has to choose a position according to a certain criterion, which depends on the positions of all the others. I'll give an example in a minute. Okay, so typically, what I want to do is to let the number of players go to infinity. Why? Let's again take an analogy with continuum mechanics. Clearly, if we want to make a predictive model, or if we want to make a model on how the temperature and the velocity of air is in that room, we have wonderful models called Navier-Stokes equations. Okay? We don't go to the individual motion of all the atoms, of the gas molecules, and all the intermediate levels. We don't need, okay, for such macroscopic, for at least the majority of the predictions that are being needed. If, okay, anyway. So the point is, what's happening? What's happening is as n goes to infinity, you have simplifications or averaging taking place. All those macroscopic equations are indeed min-field equations. If you think about the heat equation, it's a min-field equation. And so you have those fields which are being created, which are very often the results of averages. Fine. So our intuition was that what's happening for, there are centuries of modeling in continuum mechanics, in physics, and so on. All those effective description at a macroscopic level for a continuum of objects could there be some similar features, similar properties happening in the context of game theory? Because game theory, it's like n-body problems. Huh? Classical n-body problems for classical mechanics, as n is, let's say, well, much before 10, it becomes almost insolvable. We still don't know if the solar system is stable or not. Okay? And it's not a huge collection of bodies. Quantum mechanics, if you don't rely on approximation, I have an expert, I should be careful. But if you want to do numerical simulations, you are very much limited in the number of particles you can really use. Then you have all kinds of approximations, like in quantum chemistry and so on. But if you want to do the exact simulations, the exact numerical simulations, this becomes very, very quickly complicated. So the same thing in game theory. Okay, so games where you have a few players are tractable. As soon as you have, let's say, 10 players, doesn't mean anything, 10. But as soon as you have a non-trivial number of players, essentially you cannot you cannot solve them. So could it be that as n goes to infinity, does it get simpler? Of course, they have to be indistinguishable. Exactly, that in order to write kinetic equations, you'd better assume that all the particles are indistinguishable. If you were doing statistical mechanics and all the particles were different, you'd be in trouble to derive Boltzmann equation, just to give an example. It makes absolutely no sense. So of course you have variance, you have multi-species Boltzmann equations and so on, like you can have multi-population min-field games. But you need to make this assumption. So before I go to the limit n go to infinity, I want to mention the idea of Nash equilibrium. Nash is this famous mathematician that the general population became aware of when there was a movie about Nash. Of course, when you know, and I've met and known Nash for many, many years, the idea that Kevin Costner is impersonating Nash is a little, and unfortunately the reality is much worse, and his story is much more tragic than the movie, which was already not very uplifting. But anyway, John Nash made fantastic contribution in maths and published a 2 pages long paper where he defined the notion of Nash equilibria for when you're trying to, in some sense, you would like to minimize n functions of n variables. Okay, so I try to explain here very briefly what is the notion of a Nash equilibrium. It's a set of points so that if you fix all the points at this with the bars, you fix all of them, you're left for the ith problem with a function of one variable, and you want to say that the remaining variable that you have not fixed is indeed a minimum of that function. You cannot minimize n function with n variables simultaneously, so what you do is that each variable is a minimum of its own functional, where you freeze all the other variables. So it's an equilibrium because, of course, this xi bar gets into the picture in the definition of the minimality properties of all the other players. So this very natural notion, Nash even got the Nobel Prize in economics for this 2 pages paper and this notion, but it's a very important notion because after all, this is, there is a very long history of equilibrium in game theory. More than a century of ideas about how to define an equilibrium in a game. Because after all, as soon as people had understood a little bit calculus of variation and minimization, the next step was indeed to have 2 functionals and 2 variables, and that was game theory. So, Cournot, etc., etc., many people. But there are many difficulties. Nash equilibria may not exist, but the existence is very often okay. But it's plagued with lots of difficulties, like non-uniqueness, instabilities, and fake equilibria, inefficient equilibria. Okay. So, does this get any better as n goes to infinity? So, in some sense, we saw the picture in the scientific picture in John Ball's talk this morning, where basically there was a free energy with lots of minimas and so on. So you have lots of minimas. Here it's in some sense even worse, because you have essentially continua of equilibria, and some of which make, well, you may have continua in your example too, because of the, you have all rotations. But the level of the non-uniqueness here is just can be pretty awful. So what does it mean in distinguishable players? That means that so I'm player I want to find my position. So from my point of view, I have a function that depends on the position I'm going to select, and that depends on all the other positions. But from my point of view, all the others look the same. I can exchange all of the other. So in other words, this function depends on one variable and n minus 1 variables, but those n minus 1, it's in a symmetric fashion. Okay? It's still a function of n variable. But because of this indistinguishability, when I write things like that, this f doesn't depend on I anymore. Okay? You may ask yourself, well, maybe Nash equilibria with such a structure become better. I mean, you have less. No, it's exactly, this doesn't change anything about the overall picture. So then you want to let n go to infinity. And the first question you need to ask yourself is that I started with a function of n variables. How can I let n go to infinity? What is the object? I need to have a common mathematical description so that I can try to pass to the limit. Here, you know, if I use functions of n variables for each n, the mathematical language I'm using is changing for each n. So I'm doomed. So then the idea, which we are very proud of this idea, and of course, chi cerca trova, chi ricerca ritrova, was to say, well, a function of a large number of variables, if it's a function in a symmetrical fashion, I'm going to replace the variables by the empirical measure of those points. So instead of saying it's a function of xi, I'm going to say it's a function of this measure, which are Dirac points, point masses at all those points. The symmetry is automatic because the sum is symmetrical. And now it's the formulation is no more dependent in n. For each n, I have a new empirical measure. So it's a probability measure. It's something which whose formalism is independent of n. So really, what I have to describe is a function of x and m. X for my position, m for the empirical measures of all the other players. And that's a framework which is independent of n. Okay? In fact, part of the mathematical series a few years ago, I mean, that's what I developed in my courses at Collège de France, was indeed to explain how differential calculus with n variables, symmetric variable, in that sense, can be lifted in differential calculus on the space of priority measures, functions, PDEs, and so on. So that's something that I'm just saying, well, there is an f of x and m. Okay. Is this point of view new, replacing n points by priority measures? Well, afterwards, we could find some kind of obscure paper in theoretical physics where, and there is a further connection, but I don't want to go there, where the author had some vague words saying, well, I want to let, he had n particles, I want to let n go to infinity, so I'm going to use priority measures, and it should be the law of large numbers. It was vague, partly false. But he was writing things in the end which make perfect sense. And then I went further back and I realized that some people doing in statistical mechanics had used a little bit of those ideas, and the name is Grossman. Further back. But anyway, so this is in the context, and we had to let n go to infinity. So what is the problem you get in the end? That's a Nash equilibrium in a mean-field game. So what I'm going to say is that I fix all the others. All the others, what is it? It's a probability, m. What is this probability? That's the outcome of the game. Let me put my towel on the beach. Everybody has played this game, so now you have a probability distribution of the towels on the beach. So that's this m I'm looking at. Okay? This m solves the following fixed point problem, that for each player, generic player, what is a generic player? For such a simple static game, it's just x in the support of m. Because outside the support of the measure is a set of points where the measure is positive. Outside the support, the measure is 0. There is no one. Okay? So a generic player is just a point in the support. And so what you're saying is that for each player is minimizing this position when you freeze all the others. So you see that here, you're in some sense, x is in m. And when I say the others, I'm not excluding x, because that's there is this assumption in some sense of small players, and I've let n go to infinity. It's like weak interactions in statistical mechanics, letting n go to infinity. The fact that, if you had some kind of self-interaction or not, it wouldn't change anything. General existence and stability results are then possible for this fixed point theorem, a fixed point problem. You see, it's not optimization. You're not minimizing something. You're fixing m. You minimize. You find all the set of minima, and they have to lie in the support of m, like in Nash equilibria fixed points. So then you can prove that you have general existence stability results, and you can have uniqueness when it's monotone. So let me give an example. So it looks more complicated than it is. So don't look at the formula. What I have here is a function of xi, which is to say I want to choose my position according to a certain function f that I minimize. So an example: we go to the beach, put a towel. There may be places of interest where we can have a drink, where we can eat. Okay, so this f of xi would be the distance to those places of interest. Okay. But then I may want to avoid too crowded places. Or I may want to be in a very crowded place. So typically, how do I measure? Well, I have a characteristic length, this epsilon. If it's on the beach, it's 10 meters or something. I'm counting the number of people in the ball centered at my position of radius epsilon, and it's a double frequency, both spatial and with respect to n, so I'm normalizing this number as written. And there is this g function which is going to tell you how much you are averse to crowds or how much you like crowds. Okay? So as I always say, most people, normal people, when they go to the beach, most people when they go to the beach tend to avoid crowded places. Okay? But of course there are abnormal people who like to be in a very crowded places, and they have a name. They are called teenagers, right? So let's see the effects of teenagers against normal people. And the point is that when you want to avoid crowds, you have a unique minimum. If you want to go in a crowded place, you don't have a unique minimum. And that's very easy to understand. Suppose that you have two places of equal interest, and people want to go to be together. Well, they're going to mass either at one point or the other. Two solutions, obvious. Okay? It's time to wrap it up. So before I do that, just to show, in a very particular cases, what a min-field game is. So I didn't want to start with this slide because that would have been a little bit worrying, but the type of equations which are involved can be pretty tough. What do I want to say is that indeed these type of non-linear equilibria leads to many new mathematical issues, and let me tell you a story. So I'm almost done. Let me tell you a story about a simple example. Okay, I'm shutting down the computer, and there's still something on the screen. Nah. Okay. So we had many applications. We had a startup which worked very well on data and social networks and so on. And that's very much related to what I'm mentioning here, because after all, those are huge numbers of players interacting through social media. But anyway, we looked at one example, and I want to conclude with this example. It's going to take 1 minute. We look at an example just to explain how one uses these models, which was the example of the OLA. You know what the OLA is? Good. Okay, so the OLA is indeed people go to a stadium, and certainly they, from time, for reasons unknown, they're not even paid to do that. They stand up, push their arms up, and this creates waves that propagate in the stadium. You should know that there is a huge literature, scientific literature on the OLA. Okay. Don't mean much. There is a huge scientific literature about any subject, so why not about the OLA? But it's, of course, an example of coordination of a huge number of people certainly coordinating. There are many examples of that sort, emergence, a theory of emergence, and so on. I don't want to go there, so we just played with this model. I'm not particularly interested in the OLA. And here is how one uses the min-field games, just to give you an example. Stadium, right, circle. We're going to say we have a large number of people in each column, okay? Rows, which are circular, columns, which are orthogonal to those circles. Typically in a stadium, you have about 100 people. 100 rows. That's a typical order of magnitude. Of course, in America, it's a bit larger, but usually in Europe, it's about 100. Fine. So 100 is pretty large. That 100 is going to become infinity in min-field games. So then we are going to say, in that collection of people on the column, what are their rationality, their interest? Well, first of all, there is a cost for moving, like kinetic energy. Moving is an effort, that's a cost, 1. 2, a cost for position. Standing, sitting is comfortable. In between, not so much. So you have a cost function for position. So the state of each player is going to be described. This is typical of control theory, system theory. You have to say who the players are and how you describe them. So I should have said that the only variable is 1, the coordinate along the circle, and 2, the position, either sitting, standing, or in between. Fine. So description through a probability density, cost for moving, cost for position, and then mimicry. I want to be in the same states than my neighbors. Okay, that's it. So, and you define that easily. So then you have a criterion. When you have a criterion, thanks to that, you have the equations. You can solve them numerically, and you can even make analytical descriptions. If you are always dealing with the same stadium, okay, then you can prove that if the coefficient, the mimicry coefficient is not small enough, there is a unique stable periodic wave up to a change of direction. so clockwise or anti-clockwise. And so in particular, you make a prediction, which is that the viola always go at the same speed. And this speed has been measured, it's the same universally. Okay? So I'm not saying it's a good model, but it's just making a prediction which is indeed accurate. In fact, you can even think of simpler model for the viola. We were interested in the viola because it's although the viola itself could be explained, but in a much easier way. It's still a good example of coordination taking place and propagation of crisis and so on. Anyway, so this is one way to use min-field games. There are many ways. If you want more details, indeed, there are lots of books which are popping up nowadays, and those videotapes that you should use with moderation only if you need to sleep. Thank you very much. I'm a little bit late. It's time for lunch, and and soon I want to conclude by saying happy birthday, okay?
Thank you very much, Professor Lyons. Although the timing is past, but I think it's better to take 2 or 3 questions, if there are any questions, before we go to the lunch. Yeah, I think there are some technical questions. It's better to share. Yeah, please.
Just curious now, nowadays many things become big data, become data-driven analysis. So in some sense is there a possibility this kind of model could actually like predict human history, aspect of human history? Do this kind of model have this kind of power?
Okay, so listen, first of all, one has to be extremely careful when saying one might apply or not any kind of mathematical theory. In some sense, I'm playing a dangerous game here. I'm advocating the use of mathematical tools and models in situations which were not thought to be amenable to mathematical modeling. So one should be very, very careful. There are also lots of ethical issues that I don't even want to discuss. But I certainly want to mention that we are conscious of those difficulties, and we are thinking about them, and we are basing our actions and the problems we look at on those reflections. Fine. So whenever someone asks me, could one use those min-field games for a new application, I would say, I don't know. Why? Because working on an application is just, well, sure, I mean, we're going to do that. It takes years. With Huawei, we had the first model that we built, it took 1 year. And we were meeting on a regular basis. It's not something that you do overnight. It has to be, first of all, pertinent for the applications, and it has to make sense mathematically, and there are things which are too complicated that you want to discard, but maybe those are the out of the matter from an engineering point of view, etc., etc. So you go back and forth, cycles and so on. So it's not a linear process from the theory to the application. It goes back and forth many, many times. Fine. So there is the issue about big data, the use of data, and so on. What I'm afraid of is that data are very often used because you have no ideas. So you are accumulating data, and now you are hoping that some kind of semi-god, which is called an algorithm or deep learning or whatever, is going to provide an answer to a question you don't know how to formulate. If you think about it, that's not okay. The good examples, and we had a startup that we sold because we could use data, meaningful data, not big data, but meaningful data, in an efficient way, which turned out to be very good from a marketing point of view. So we could measure the effects in terms of sales. So certainly one can use such mathematical ideas in big data. But what I'm really interested in, but you need to have an idea of what you want to do with your data. And when one talks about classification of images, the idea is clear, because that's a goal which has been around for about 50 years. 50 years people have discussed classification of images, so the goal is clear. Or if you think about automatic translation, it's also a goal which is clear, which has been around for 20 years. So apparently you don't need an idea, except the idea was, in fact, appeared a long time ago. It's just now there are some technical solutions which do things that we were not able to do before. So first of all, you need an idea. Okay, so that's it's always true, and it's still true in big data. Now there are many things to be said. Gérard Berry, my colleague at Collège de France, always say that in some sense, in terms of modern data analysis, I prefer to use this terminology than artificial intelligence. What has been really solved or picked were the low-hanging fruits. Okay, so those that you can pick up easily because they are in the branches which are, closest to the ground. So that's one thing. The second thing is that in many situations, people will incorporate, if you start using data and use them in the life of people, people will change their strategies. So I'll conclude with one example, which is about electricity. More and more in all countries, you have smart meters, okay, which measure everything you do with your with electricity. And in fact, it's frightening because any kind of expert looking at the profile of of what you're doing with your electricity, of what the meter is recording, can tell you precisely at what time you started washing your, you started using the washing machine. Huh? So that one can see that on the data. Okay, so the companies tell you, well, we're going to use these data. So, okay, it's anonymous, it's safe. Let's hope so. We're going to use it. We are going to use it to provide it some services. Yeah, sure. But in the end, they also want to use them for tarification. Okay? Obvious. Now, if you just use the data and deduce a tarification, what's going to happen? You propose a new tarification. Overnight, people are going to switch to new strategies incorporating those tarifications. So if you don't incorporate the way people are going to react to those tarifications, all the work you've done on data is meaningless. It's useless. So I'm not saying that the work you're doing on data is useless per se. It's the way you're going to use it. And so you need to use it with a model which will try to say how people are reacting to a change in tarification. And there are many problems of that sort. So I wouldn't say, I don't count on me to make any kind of definite statement on these machine learning, deep learning, etc. Depends, there's many problems around. There are also, the first thing you have to learn as a scientist is to distinguish between easy problems and difficult problems. So let's concentrate on difficult problems, and then I'm pretty sure that the artificial intelligence world will combine data techniques and modeling, in some sense coming back, like in all post things, coming back to some classical ideas combined with new ideas, and this will require more mass. So I don't know.
Okay. So as the director indicated,
it's a very important and long question. It's an important subject. There is so much.
It's a pity we cannot continue. So let's start the lunch, but you can discuss with Professor Lyons your question. Okay, thank you.
I'm sorry.